So the simplest examples is we said dl squared equal to dr squared plus r squared d theta square plus r sin theta squared d phi squared. And we can write this out as dr d theta rho vector d phi and then dr d theta d phi and 1 r squared and r squared sin squared theta. So this is our metric G, Gaussian metric G, which itself is a function of r theta phi in principle. Well, it does not have phi in the present case, but it could be. So this is why you need this Gaussian trick of introducing more general kind of matrices as the metrics rather than just the Pythagorean one. Okay, so so when we say that the inner product is left invariant by the ON groups, we can think of all the three different ways. The most general abstract way, which simply thinks in terms of inner product, or we can think of the matrices, specific matrices, row and column matrices, and write O transpose O in matrix language and say it is identity, or we can think of it as having a general Gaussian metric G. Even then we can essentially, the group we will get is the same because it keeps that matrix invariant. But so I should correct myself. So the SON group is specifically the one that keeps the for ON. So I may as well draw a line here, and SON is to use Pythagorean metric just call it delta and say that O transpose delta O equal to delta. That is what that statement written in terms of indices means, is essentially that, where we inside did not put delta. So all this song and dance I did to tell you is that actually it is O transpose times the metric O keeps the same metric. So that is the geometric meaning of the transformation. But since we make the standard choice of the metric being delta, it just looks like this, okay, but it keeps that matrix invariant. Now that allows us to say what happens in the Lorentz transformation case. It allows us, it meaning the Gaussian notation. Gaussian version, but still in its simplest form. To introduce Minkowski metric, which is 1 minus 1 minus 1 minus 1 0 0 0 So, I am thinking of this eta as some kind of a g, but I still made it simple enough that there are only 1s and minus 1s in it and they are on the diagonal, but there is a sign change unlike the Pythagorean one. And then we say that Lorentz transformations or Lorentz group is the set of matrices such that lambda transpose eta lambda equal to eta. The lambda matrices constitute the Lorentz group. Index notation, we say lambda mu nu, I hope you like Greek letters, mu rho, lambda rho sigma equal to eta nu sigma. So, this is how you will often see it written, but the invariant kind of statement is this. Even that is not all that invariant, because actually it is still a matrix. Here we have written out all the indices. Okay. So, this is how it is usually written, and the eta matrix is written with both indices down. This is the standard notation. People also introduce the, I mean, more advanced things are possible with it, but for our purpose this is what the group is going to be. This group, because of the one sign opposite to the other three signs, is called SO31, special orthogonal group of, and so after imposing, also impose determinant lambda equal to 1. So, this leaves out space inversions and operations like that, which have a negative determinant, mirror reflection, things like that. Also impose determinant lambda equal to 1. This is called SO31. Special orthogonal group with 3 positive signs and 1 negative sign, or 3 negative and 1 positive, it does not matter. So, it is just called SO31. Okay. So, next we do a little bit of abstract stuff again and then come back to this, or I should introduce one more group before we go on. Yes. So, while we are introducing groups, let us do two things more: unitary groups and symplectic groups. UN and SUN, they are actually C, but the C is hidden because unitary generally means Hermitian U dagger U equal, its unitarity is already on complex matrices, so nobody writes C for them, but they are complex groups. So, they act on a vector space that allows scalar multiplication by complexes, and here we need to introduce the inner product for complex vector space. Which has the property that x y is equal to y x star. Okay, so, we need to do this to keep things meaningful, because so this ensures actually the positive definiteness. So, for example, if I have a vector z which is say z1, z2, z3, then zz will be equal to z1 star. So, it will be mod z1 squared plus mod z2 square plus mod z3 square, right, because this star effectively means that you have to construct the inner product zw to be equal to z1 star w1 plus z2 star w2 plus z3 star w3, and it ensures positive definiteness. Also, we have that x comma ay is equal to a times x comma y, but ax times y is equal to a star comma xy. So, your scalar, so a belongs to complex numbers. The scalar by which you multiply your vector, scale your vector, if it is, whether it is multiplying the second entry or the first entry of the inner product matters. Later on in quantum mechanics, Wigner defines antilinear transformations where it is the opposite. It is when it is taken out of the front factor, it is complexified and not if it is. So, that requires, it is some very special thing that is required for time reversal operations, but this is good enough for the time being. So, these are the properties of the inner product. So, these are salient features, and then it is easy to define what is unitary and what is not. I mean, what is unitary and what is special unitary simply says that in matrix notation, is simply u dagger u equal to 1 identity matrix, and special unitary additionally determinant u equal to 1. So, here note u dagger u equal to 1 implies that determinant of u dagger u, which by theorem of determinants is same as determinant of u dagger times determinant of u, becomes star of determinant u, because when you dagger you transpose and you complex conjugate, but transposition does not change the determinant, but that starring will remain. So, the determinant will basically be the star of the determinant u, and therefore, you get mod det u mod square, this equal to determinant of the right hand side, which is just 1. So, this implies 1 equal to det u squared. So, det u is in general e raised to I theta with some real theta. The special unitary requirement sets theta equal to 0. it has to be 1 only. In the real case, it could be +1 or -1. The orthogonal groups without the S condition is plus or minus 1. The complex groups without the condition can be a whole continuum of possibilities, the whole circle. So this brings us to a very broad distinction between various kinds of groups. So we now get to some topology. We will introduce the idea of connectedness and simply connectedness. Oh, I still didn't introduce the symplectic group. We'll do it at some point. Okay. So connectedness, we simply say that. So very simply speaking, let me just draw some pictures first. Connected simply means that any 2 points within the set can be joined by a curve which lies entirely within the set. That's all it means. Okay. Or actually 2 elements, but we are already thinking geometrically. So 2 points in the set can be joined by a curve lying in the set. So if I draw this disk and I draw 2 disks, the disk is a connected set because I can always draw a curve connecting 1 and 2. But here if 1 is here and 2 is here, then I can't connect them. So this is connected, this is disconnected. Okay, so this is the very basic intuitive idea, and to formalize we say that given elements G1 and G2, there exists a path parameterized by some parameter T. So let us be specific to matrix groups. Given matrices G1 and G2, if there is a path, by which we actually mean a continuous mapping of the interval 0, 1 into G of T with T belonging to the closed interval 0 to 1. That is the meaning of this word path. The word path means this map. From 0, 1 I have created a map into the group such that at 0 it becomes G1 and at 1 it becomes G2, such that G of 0 is equal to G1 and G of 1 is equal to G2. So this of course has to be, if you write out the matrix as an array, then this has to be true for every single entry. Entry by entry you should be starting with this entry in this matrix and ending with entry in that matrix. So in component notation, every entry of the two matrices can be correspondingly connected. I am just keeping it short. Now this immediately, I mean, so far we are just talking some topology, but we see immediately the application that if you take the GL groups, then the GL and R groups are not connected. Has matrices with determinant either greater than 0 or less than 0. Right, because we excluded determinant equal to 0, because determinant equal to 0 will not allow inversion. So there will be no inverse existing and it will not have group structure. So the fact that it has group structure means that you have excluded 0, but that means that because the determinant is just lying on the real line and you have excluded 0, so these are plus side and minus side and 0 is excluded. So there is no way of going from one side to the other continuously. So all the matrices lying on the left side are connected to each other and all the matrices on this side are connected to each other, but not to each other. Thus determinant less than 0 are all form one connected set, one connected subset, while det greater than 0 form another connected subset, but the two subsets are not connected. I should have said plus and minus. To each other. Rather elements of, okay, plus and minus subsets. So the GL and R is a not connected set. Which side will you like to be on? They are both equivalent, right? They are both mirror images of each other. But which of these will form a subgroup? So the one on the which contains a plus will be the subgroup. So if sets are called minus and GL and R plus respectively, we see GL and R plus forms a subgroup. But not GL and R minus, although they are isomorphic to each other, but the other one will have a negative of the identity which we don't accept as identity. So, but now let us look at the GL and C. The story is different. What happens here? The determinant is a complex number. So, the determinant values lie in the complex plane with 0 excluded. I think sometimes mathematicians write something like this. C with 0 excluded, only one point excluded. See how much excitement can be had by removing just one point out of the plane. And remember, the point has not even any area. So, if you exclude 0, then you can make it into a group, and therefore, the determinant values lie all over the complex plane. Now, this set is all connected because you are allowed to, it is not that line, when you have a line and you remove a point, it becomes two disconnected pieces, but the plane with one point removed does not become disconnected. So, here say so here all points which are actually matrices can always be connected. Since we are physicists, we will not ask for a proof for it, right? In complex plane, you can connect anything to anything, but if you are mathematics, you have to prove it. Okay. So, GL and C is not connected, is connected, whereas that one, the GL and R are not connected. But there is the next distinction, simply connected versus connected. So, simply connected means that if you draw any circle in the set and you can shrink the circle to 0, such sets are called simply connected. So, the simple thing to say is that if you take the corridor outside and the classroom together as one set, then it is not simply connected, because you can get out of this door and enter through this door, and that circle cannot be shrunk to a point. You cannot continuously, if you are only inside the classroom, you take any circular trajectory, you can always make it shrink to 0. But if you include the outside corridor, not a larger thing we do not know, but if you take the outside, only the outside part, you can enter through one side and leave through, leave through one side and re-enter through the other, then you get a non-simply connected trajectory. So, we will see that the GL and C, although they are connected, they are not simply connected, because that point 0 has been removed. So, there will exist two classes of curves, a class of curve which does not go around the point 0, those curves can all be shrunk to a point, and the class of curves that go around 0 and then cannot be shrunk to a point. These things, this kind of thinking developed only around 1900s and later, it's called topology. One of the pioneers was Henri Poincaré, and he was also thinking of trajectories in the phase space and the various categories of trajectories that can happen and so on. So some of the classical generalities of classical dynamics were also couched in this language. So yeah, so this started with those kinds of reasoning, and it's today part of topology. So the idea of simply connected is that given a closed curve lying in the set, whether there exists a sequence of closed curves which converts the or deforms the original one to a point and there is some formal way of saying all this, which is right. So simplest way of thinking about it is to, I will not write out everything because it just is a bit lengthy and not so illuminating. Suppose we draw two such things, two curves, and put a parameter T1 on this, S1 on this, and put parameter S2 on this. So both S1 and S2 go from 0 to 1. That makes each of them a circle. But now we also introduce a parameter T at which we construct intermediate circles. So if there is a path which we saw earlier, what we didn't write it out. We wrote this G of T. Yes, so for matrices we wrote G of T. So now we say similarly, if there is G of S and T such that G of S comma 0 with of course T belonging to again 0 to 1 such that G of S comma 0 becomes equal to G1, now I have to put 1 somewhere else, G1 of S and G of S comma 1 becomes equal to G2 of S. So I call this curve G1, the inner one should be G1 and the outer one is G2. So I have a curve G upper index 1 and it is put in bracket because it is not really important as a number, it is just a label, okay, whereas these are important as numbers. So this is just labeling one possible curve whose parameter is S1. So, G becomes equal to, you can, I do not want to muddle this up, but there is a more general map with two parameters S and T, with T running 0 to 1, S running also 0 to 1, such that if I ran over all the parameter values, I will be covering this whole annular region. Okay. Now, these two are said to be deformable to each other. And then we say that a set is simply connected provided or deformable into each other. A set is simply connected provided every possible closed curve in it can be deformed to the trivial closed curve to a point some fixed point, a given point, okay. Some P0 given point. For all values of the parameter, it is just the same point. So, if every single every possible is a important thing. Every possible closed curve in the set should be reducible to a point, then it is called a simply connected set, and if it is not, then it is not simply connected. In fact, in topology, some very interesting things are done based on this, which is that when you do not know too much about a space or do not want to become too specific. So, topology studies point sets in their most generality without imposing too much structure like length and angles and anything. So, if you just want to know the properties of a set, you, like casting a net, you throw all possible circles you can throw into it and check how many of them can be shrunk, and then there can be non-shrinkable ones, but independent non-shrinkable ones. So, if you take the surface of a torus, then you can of course draw little curves on it which can all be shrunk to a point, or I mean you can draw even a big one, but such that it shrinks. But you can make a one that goes around one of the circumferences which can't be shrunk because it is stuck like this. But you can also draw a circle that runs like this, and that also can't shrink because it is stuck around this circle. So, there are two inequivalent circles which cannot be shrunk to a point. By studying all the possible circles that cannot be shrunk to points or cannot be deformed into each other, you can classify the space. So, this is called, and actually the beautiful thing about it is it actually has a group structure of its own. So, it is called homotopy group, and that captures the, it is called the fundamental group of the set. So, maybe later on we will come to fundamental group. generalization or homotopy group H1, which should suggest to you that you can also define H2, H3. You can classify a n-dimensional space by casting spheres spheres of size n, dimension n into it, and see whether they can be shrunk or not. So that essentially captures the topological, the connectivity aspects of n-dimensional spaces, even when you don't care about anything else. Okay, so for the time being that is okay. So we saw that, so did we assert that therefore the GL and C is not simply connected? Okay. The next thing I will do is what I missed in the middle, which was introducing the symplectic groups. Classical, not A, okay, classical groups, part of. This is the case when the metric is a funny one. It is not diagonalizable, but it is skew symmetric. Metric. And now this metric is actually very doubtful. Do you really want to call it a metric? Because when it is skew symmetric, it means that x is 0. It has the property that xy is equal to minus yx. So it has no magnitude notion in it actually, because xx will always be 0. So it's not considered an inner product. It does not qualify to being called an inner product, but it is still a metric in some general sense. It's a bilinear form, so this is an antisymmetric bilinear form. The ones that classify as inner product are symmetric bilinear forms, and this is an antisymmetric bilinear form. So what happens in this case is that, so typically the metric in this case we call epsilon. It has 2 by 2 blocks n such blocks, but each block is 2 by 2 and in it reads 1 and minus 1. And everything else zeros. This is one version of writing. There are other versions where people will put put entirely along this off main off diagonal, minus ones and plus ones. You can recast it so that it goes all along this way. But this is a most convenient one because it remembers which element is related to which. So, okay, so this is what the metric looks like, and this is what it is left invariant by the elements of this group. So, so suppose, so in what did we call algebraic or index notation? What is the time? Okay. Let the vectors be carrier space. Have components psi A with A equal to 1 up to 2n. We need an even number because we have to make it antisymmetric in each block. Then what we need is and suppose we let psi A prime be equal to some transformation matrix beta AB psi B, sum over B up to 2n. And what we need is that we are given psi A psi B, this inner product is equal to epsilon AB, and need psi prime C psi prime D also equal to epsilon CD. So what this does is that, so the point is that this betas I can pull out of this, and what I will find is that beta, I will cheat by looking in my notes because time is a little short. So beta AB epsilon BC and beta DC equal to epsilon AD. So this is the requirement that the beta matrices have to satisfy. So beta matrices satisfying this are called SP2n, SP twice n, yes, and which real. And it is called symplectic group. And by default dimensions are even numbered. So we'll stop here today. So, we will see that the SP true n groups are groups of invariants of canonical transformation.